And we'll get started from the current slide. All right, we are now recording and where we need to be recording. Any questions on anything we've done up until now? Okay. Well, we finished with sound, pitch, some of the things like this, the inner ear, the outer ear, all the workings there. And we're getting ready to start in 16.4 on page 439, and this is talking about the Doppler effect. Now, this is something that's a fairly common, you hear about it a lot these days, especially this time of year when the weathermen are on telling about severe weather. They're always looking at their top Doppler radar to tell if they can pick up any rotation. Because the radar, of course, sends out a signal, a lot like sonogram does, sends out a signal and then it gets a reflection back. And what a Doppler radar does is measure the differences in the timing of those responses. And if you've got circular motion, if you've got straight line wind and the radar is sending out a signal and then it's bouncing back, and all of it's coming at pretty much the same velocity to you, that indicates one thing. But if what's coming back to you, if some of it seems to be going slower than others are going faster, that would indicate rotation, okay? Because this side of the storm would be coming at you and coming back quicker, more quickly, and this side would be taking longer to go. That's what a Doppler radar does. That's what the Doppler effect is talking about. Now, if the car is moving from right to left here, observer A, the guy standing over here, in front of the car, hears the car horn at a higher pitch than the driver, whereas observer B hears it at a lower pitch than the driver. The driver is in the car and the driver hears it, okay? Now what the driver hears is exactly what's coming out of the horn, okay? But what observer A is hearing, because the car is moving this way, and remember, sound waves are pressure waves, okay? And what you're hearing is the frequency of that pressure, okay? And if the car is moving this way and the pressure waves from the horn are moving this way, then the car is compressing these, giving them a higher pitch, okay? This guy in the car, or guy, gal, whoever it is in the car, is hearing the actual pitch because he's in the car. This one, however, the gal over here, is hearing a lower pitch because the car is moving away from her. This wave front gets to her, and by the time this one gets to her, the car has moved this way, so it's further away. So this is a lower pitch that she hears, higher pitch that he hears, and then the actual pitch is what the person in the car hears. That's what the Doppler effect does. Are any of you Big Bang fans, the television show? Okay. I remember one time Shelton went to a costume party, and what he wore was a T-shirt with a wavefront on it like this, and they said, well, what did you come up as? He said, the Doppler effect. Of course, no one at the party knew what the Doppler effect was, and he tried to explain them, and they disappeared really ely with his explanation. I'm glad y'all stayed, but never mind. Okay. Now, 1627. That is pages after pages after pages from here. This is 16.6 is the next slide. So I'm going back to this slide and try to fill in the gaps. This is not the best PowerPoint that I've ever seen in the text. Okay? By the way, the variation in pitch is called the Doppler effect, named after Christian Johann Doppler, physicist and mathematician born in Austria, best known for this phenomenon that is described here. So, Austrian physicist and mathematician. All right. Here is the apparent Doppler shifted frequency for sound as given by this equation. Got to find some part of the slide here. I think maybe this will do best up here. Let me get my pen. All right. And by the way, the Screencast-O-Matic was doing, or the pen or something was really wacko both of my first two classes today. Today it seems to be better, but we'll see if it continues. F prime is equal to F times V divided by V plus or minus V sub S. Okay? Now, what do those things stand for? F prime is the Doppler shifted frequency. F is frequency. Okay. F is the actual source frequency. Okay. Okay. V is the speed of sound. Speed of sound. And V sub S is the speed of the source. Okay, so in this figure, this would be V sub S, the speed of the source. Okay? The actual frequency of the sound, this would be, what he's hearing is F. Now, what this guy, that's the driver. What this guy is hearing is F prime. What she's hearing is F prime. Okay? But it's different frequencies. So where do you get that? It's plus or minus. I think I said it and forgot to write it. Okay? V plus or minus V sub S. Okay? Now, if this is V sub S, the one he hears is F prime is equal to F, the frequency of the source, times V over V minus V sub S. Because obviously the speed of sound is greater than the speed of the vehicle. Now, unless this is a jet airplane. It's not a jet airplane. We're not dealing with jet airplanes now. We're dealing with things that travel at slower than the speed of sound. Okay? So, you would be dividing or multiplying this frequency by the speed of sound divided by something less than the speed of sound, V minus Vs, and that would give a larger frequency than what the original frequency was. Because when you divide by a smaller number, it's the same as multiplying by a larger number. Okay, you understand that, right? Like, let's just say the speed of the source was 1 miles per hour, and one. Okay, we won't give a unit. 1, and the speed of sound was 10. 10 over 9. Okay, 10 minus 1 is 9. 10 over 9 is more than 1.1, but it's a number greater than 1. So then the frequency he's hearing is greater than the frequency that the driver hears. Over here, her F prime is F times V over V plus Vs. Because now the denominator is greater than the numerator, same numerator, but the denominator is greater, so it's a fraction less than 1. So her frequency that she's hearing is less than the frequency of the source, of the actual sound that's being emitted by the horn. Okay? The plus sign in the denominator is used when the source is moving away from the observer. The minus sign is used when it's moving toward the observer. And just remember that by what makes the denominator smaller, that's going to be when it's going toward the guy. What makes the denominator larger is when it's going away from the listener, observer. Okay? So that's how you use that formula. Plus if it's going away from you, minus if it's going toward you. Minus will always increase the frequency, preserve the Doppler frequency, and the the plus would decrease the Doppler frequency. Okay. And that's the figure that you see at the top of page 440. Okay. I don't know why, but they have a blue car in the book and a green car here. They have orange-looking lines around. These are black. I don't know why it's not the same. Okay, so let's do example 1. If there are no questions on that. Unfortunately, we don't have much room to work on this, so I'm going to have to erase what's here. Hopefully you'll remember what the convention says to do. An automobile sounds its horn while passing an observer at 25 meters per second. So what would that be? 25 meters per second in the terms that we just had on there.
As a V, how do you say
It is V sub, it's not an F. Meters per second measured.
S.
Yes, the V sub S, the velocity of the source. Very good. The actual horn frequency, so that's going to be what? F. The actual horn frequency is 400 hertz. 400 hertz. And they put a bar over the second zero indicating 3 significant digits there. Now the speed of the source is only 2 significant digits, which is, you know, why didn't they just put the first 0, because you're not going to use this. But anyway, we'll go with it. Assume the speed of sound is, what would that be? Speed of sound is what? It's the letter V by itself. S here is source, not sound. V is 345 meters per second. Okay. And if you go back to probably what the table 16.1 on page 437, we see that the speed of sound in dry air is about 331 meters per second, and it increases by 0.61 meters per second per degree. And since this is another 15 degrees beyond that, this must be quite a bit warmer, okay? Because you multiply by the temperature, so it must be quite warm, okay? 345 meters per second, okay? Now, what is the frequency heard by the observer while the car is approaching? So this will be the the F prime, that's what they called it, while the car is approaching. So this would be like the guy A here. So what would that be? Okay, you would use the minus, so it'd be F times V over V minus Vs, okay? Which would be frequency 400 times the speed of sound, 345 meters per second, divided by the difference between that. And if you take 345 minus 25, that's 325 meters per second, okay? And if you will do the math there, 345 divided by 325, and then no, 320. Sorry. Minus 25, 320. I was going, something's not right here. 320 meters per second. 345 divided by 320. And you notice the meters per second cancel out. And this is multiply that by 400 hertz. And that's how many hertz you'll get. So how are you hertzing?
431.25.
431.25. Let's just leave 431 hertz. They may just round that to 430. No, they use 431, even though they only had 2 significant digits in the V sub S. So evidently they're not worried about that now. They used to be, but they're not anymore. And then it says, what is the frequency heard when the car is leaving? So the car passes him, and now it's leaving. Now he's in position like B over here. So the frequency as it's leaving is F prime will equal F, same F, the original F, the F of the horn, not the F that he heard before, the previous F prime, the F of the horn, and that would be 345, but this time we're adding 345 to 25, which I think is 370, right? Both of those being meters per second. Okay, and this was your 400 hertz times that factor there, and what you get the frequency once it passes. .345 divided by 370 times 400. 372.97. Let's just call it 373 hertz. Okay. All right. So, a fairly significant difference there. Okay. Now, I don't know if you've ever noticed this when, say, if you're standing near when a train's coming at a pretty loud rate of speed and he's blowing his horn and you hear, you know, you'll hear that drop when it passes you. He's not changing his horn any. It's just that you're on the front side of the Doppler and you're on the minus sign there because the difference is what you use in the denominator. And then when he passes you, you change it to the plus sign in the denominator, and now the frequency is less than what it was before. It's pretty significant when you're listening to it right there at the change. So 373, that's what they got as well. It says the Doppler effect can be easily demonstrated by 2 students and a toy horn. One is the observer and one remains stationary, The other with the horn blows it while turning around. The change in pitch heard by the observer is the change in the Doppler effect. Now, what you will be dealing with, page 441, ultrasound. Here's your physics connection here. Nice little blurb here. Ultrasound is used to examine tissue and liquid-based internal organs and systems without subjecting the patient to invasive procedures. A very good thing. Ultrasound is an extremely high-frequency sound ranging from 20 kilohertz up to 5 megahertz. Okay? Now, I see and read those numbers and I think, couldn't that be damaging the little bitty eardrums of that fetus that you're doing? Obviously not. Okay? Evidently this is way outside the range of anything that would have any effect on this. But you know, they just don't use it on fetuses. That's the most common thing. I can't remember how many years ago now it was. I think it was 2008. Possibly 2000. No, wait. Back up. I don't remember. It was a while back anyway. I had a young doctor at the time who seemed, this isn't fair to say, but he seemed nervous. Not nervous around me or anything, but just nervous he might miss something. And that's what, he looked young, and I figured he was fairly new at it. And on, I guess, a routine, and I didn't know Dr. Julie did this, but we had an examination. I mean, he did urine sample, everything, and he said he saw microscopic blood in the urine. Okay, therefore he was almost convinced it was probably going to be bladder cancer. So therefore he sent me in for an ultrasound of the bladder. Okay, and actually I'm thankful he did, though it was completely unnecessary for that. They did it, and the technician, they said, come in with a full bladder and drink the dye and that kind of stuff. So it was really full, and she looked at it and said, everything looks great here. Why don't you go to the bathroom, because I can tell you need to, because I took them at their word. It was a full bladder, a very full bladder. But she kept scoping around just because she was doing it, and had all my stomach all greased up and everything else. So she kept going. She said, I kept hearing these Usually all these don't mean something good. So I said, is something wrong? She said, well, I don't know what it is. It looks like some sort of a shadow near one of your kidneys. Now, it may be nothing. It may be flatulence. It may be anything. So I don't know, but she went and got her supervisor. And he came in and went, So they decided to have me do some more tests. And I believe it was probably a radioactive isotope they put in, and did further tests, and found out that I had, y'all probably have heard of this, angiomyolipoma. Angio meaning blood, myo meaning muscle, and lipoma being fatty tissue. And I think I probably have one on my arm here. It's just a little lump that moves around underneath. I think that's probably what it is. It doesn't do anything. It just sits there. But they said my kidneys, both of them, were surrounded by these things. Just tons of them. I just had them all over the place. But one was big and looked like it might be growing. Of course, this is the first time they saw it, but it looked like it could easily be, doing something. And they said, we need to get that one out, because if it is expanding, at some point it can't expand anymore. It might rupture, and then all that blood will be spilling into your cavity there. Is that the peritoneal cavity or whatever it is? And you could bleed to death before we ever get you. You wouldn't have any indication it had happened, except you start feeling dizzy or sick or something. And, then they'd have to take you to the emergency room. By the time they had figured out what it was, you'd probably bled to death. So we need to get it out. So I was sort of glad I had a panicky sort of young doctor, but I got rid of him after a while. Well, no, not right then, but a little bit later. But anyway, I was referred to a urologist at UAB. Actually, friends of ours had used them for their parent, and they were so pleased with them, and they wanted me to have them. He wasn't seeing new patients, and they went to him. They were MDs themselves and said, look, you got to see, blah, blah, blah. So he took me as a patient, and that was his diagnosis. They went in and took out that one, and it was actually had grown about from the time they had first seen it, and they had to take out they thought they would take out half my right kidney. They had to take out more than half. So anyway, they got it. So they went stem to stern around here. I mean, said, how many people did you have in there anyway? He said there were a lot of hands in there, but they were trying to save the kidney. If they had done, is it sort of a liposuction type thing, that they could have just gone in through a little incision and sucked out the whole thing, that would have taken the whole kidney too. Said they wanted to leave as much kidney functioning as possible, so they went in and did a pretty major surgery. So that was my ultrasound, and pretty glad that they were able to detect it. And then later, after the surgery and all this, I was seeing the urologist periodically, and I asked him, well, by the way, I said, the guy said he saw microscopic blood in the urine. It's called uremia or something like that. It had a name and it meant microscopic amounts. He said, oh yeah, I can see that. I said, well, he was worried that might be so. He said, oh no, I wouldn't worry about that anytime. That's so little, that's normal seepage. So all that was caused by a false alarm, but glad it happened. And it made me wonder, because I had an aunt, my father's sister, his younger sister, had died of some sort of internal bleeding that they, as far as I know, they never understood where it came from. They assumed it was an aneurysm, but I wonder if she had a bunch of these and one of them ruptured on her. And if they didn't do an autopsy, I don't know that they did, they never would have known what. They just assumed it was an aneurysm when it probably, I just wondered if it wasn't. So anyway, my ultrasound story, that pretty thankful they knew what they were doing. Pretty thankful y'all are going to know what you're doing. I assume that's the kind of stuff y'all will be doing. Is that right? No? Oh, yeah, you won't be. That's right. Yeah, but the rest of you, that's the kind of technician you're studying for. Okay. So I'll let you read the rest of this. The device sends, well, I'll read parts of it. A transducer sends sound waves from a particular frequency, measures the frequency of the waves reflect off the various media and organs. Since the speed of sound is dependent on the, and here's Kima. Okay. I do have your second test for you if you want that. So
I saw it last time.
Huh?
I saw it last time. You showed me last time.
Huh?
You showed me last
Oh, yeah, but you can have it now because I've received them all in. For some reason, my pen's not writing. No, there it is. Okay. It's not wanting to mark you here. Maybe you're not here. I don't know. Okay. We're just talking about page 441 in chapter 16, ultrasound, which is exactly the type of thing y'all are going to be doing, I take it. But the device, okay, measures the frequency of the waves reflected off the media. Since the speed of sound is dependent on the medium through which it travels, the ultrasound processor takes the information from the device can determine the position and density of the tissues. So that's what it's looking at. I was telling a story. I had a growth on a kidney, a bunch of them, but one that was big, and they removed it, but they could tell on the ultrasound it was a shadow of something, and then they did a more thorough diagnosis using other techniques. The ultrasound processor takes the information from the device that can determine the position and density of the tissue. The ultrasound is often used for diagnostic purposes in place of x-rays because it does not use true radiation, is safer for the person and or the fetus being examined. Along with the monitoring the status of the fetus, blah, blah, blah. I'll let you go on with that. Ultrasound is not used to view bone structures because the high-frequency sound waves reflect well off only the liquid-based objects. So recent technological improvements in ultrasound have led researchers to advances in three-dimensional imaging and the Doppler ultrasound, where the movement of the blood can be monitored using sound waves. And this, and by the way, would be monitoring what they call Poisson flow, which is the blood flow through very tiny blood vessels like capillaries. This is showing, I guess, taking the ultrasound of a fetus And there's a picture of that too, the three-dimensional ultrasound of a human fetus. That leads to problem set 16.4. There are 19 problems there. I think the odd numbers are in the back. The answers are in the back, so you can do any of those odd numbers you wish. All right. The next topic is resonance. Now, I don't know what y'all are training for. I know ultrasound is part of it. Would MRI be a possibility? What's that? Not really. Okay. Yeah. What y'all are doing for is cardiac? Okay. And they don't use...
I think we're doing more like the ultrasound part.
Right. Just the ultrasound part. Okay. Because the other, I don't know if you know what MRI stands for. It's magnetic resonant imaging. Okay? Resonant is what we're studying in 16.5. And so we'll just go through it quickly if you don't think this will be a part of your study. Is that right? Any of you? Do you need? Okay. Okay. But they said you needed it, so we'll go through it quickly. Okay? The natural frequency of an object are basically the vibrations that it would naturally occur at. You know, that would be according to the shape and size of that. If you're talking about a guitar string, you know, plucking that depends on the tension in the string and where you put your fingers on the frets to give you the wavelength. Okay? Now, resonance occurs when the natural vibration rates of two objects are the same and they reinforce each other positively. Let me give you sort of a dumb but true example of this. Okay? Have you ever tried to push off a car? Say the car died, the battery's dead, and you're trying to jump start it by pushing. Okay? You just stand there and lean on the car and push as hard as you can. Now, what do? Yeah, you get it rocking. Okay? You push and you just get it to move a little bit, you let it come back, and just when it starts to roll back again, you push again. And what you're doing, you are taking advantage of the resonant frequency of that car. Mary's here. Now this is resonance, not residence. Okay, resonant. Okay, frequency of the car. And after a while, you keep doing that, and then you push, and then the car gets going. Then you don't have to push as hard. Okay? And you get it going, and then whoever's inside pops the clutch enough where you can get it started on that. You probably have done that. Don't try it going uphill. Try to do it downhill, okay? It works a lot better that way. Okay. Now, that's not the only case. And I've actually heard this. I don't know if it's really true, but, well, I've heard several examples of it. If you've ever seen these sort of rope bridges that go over gulches or things like this on hiking trails, things I don't like to cross, okay, I leave my fingerprints in the rope, you know, because this is hanging on so tight. Evidently, my wife's brother's 3 kids were hiking somewhere and got it. The 2 older kids always picked on the younger one. And, you know, they were bigger, they, always picked on him. And little Josh was the baby, and they thought he was pampered, you know the whole story. But he found out that they did not like walking, either one of the sister or brother, liked walking on this thing. They didn't like the shaking. It didn't bother him, so boy, when they got on there about the middle, he just started jumping, you know, and the more he jumped, if he got in the resonant frequency of this thing, he had them hopping, screaming, yelling at him, threatening his life, you know, and he was laughing his head off because he was finding the resonant frequency of that and getting in with it. So they were just bopping all over the place there. Not a good story at all. But he still likes to tell it. Okay. There are other things, and here's one. Have you ever actually watched someone tune a piano? Okay. What they do, and actually the same goes to guitar. Any of you ever watched someone tune a guitar? What they do, they're trying to listen to it, but they also, if they can get the same frequency of, and on a piano they use a tuning fork, and they have one for each, well, maybe not each string, but certain ones of the chords there, and it's the same principle. You adjust the tension in the chord, and that determines the frequency. And when they get on, you can actually, it's not just that it sounds different, it reinforces. And it's a fairly major thing. And one will reflect off the other one. And here's Deanna. All right. And by the way, I do have the second test. Everybody's turned them in, so I'll return those to you so get it right after class. Okay. So that is resonance. And I don't know if you tried this, if your mom or grandmom or somebody like this has some actual crystal drinking glasses, wet your finger and rub around the top of that, and you can actually, what they call, make it sing, because you're reinforcing the resonant frequency of that. You're making very little vibrations between the your fingerprint, going around there, and it actually increases the frequency of it. Not increases it, it resonates. In other words, it reinforces the frequency. Now, there is this one other example, and this really happened. It was called the Verrazano-Narrows Bridge, I believe in Portland, or somewhere in Oregon. Went across a big gulf, right out there in the Pacific. And the engineers had designed this bridge, and had all the things, it was, I think, a suspension bridge. But the wind on the Pacific, well, I don't know if you've ever been to San Francisco, it's always windy. The wind just comes in off the Pacific at almost the same speed all the time. It just never seems to stop. Now, there are some days that change a little bit, but there's prevailing winds, and they're almost always the same. And the designers of this particular bridge did not take into account the wind and its natural frequency. So they designed this suspension bridge, not as big and major as the Golden Gate or something like that, but it's that type of bridge. And then the winds came in, and it may have been a little bit more or less than what is prevailing, but something. But they started, and the motorists who rode on the bridge called it Galloping Gertie, because their car just felt like it was doing this when they were driving across the bridge. And one day a storm came, or a windy condition came, and it was blowing at the natural frequency of the bridge, and the wind coincided, and the bridge started literally gapping. And they took pictures of it, and you can see it. If you can find it on a YouTube video, it's the Verrazano, V-E-R, one R or two, I don't remember which, Verrazano, Z-A-N-N-O or Z-A-N-O, something, Narrows, N-A-R-R-O-W-S, bridge. Verrazano-Narrows Bridge. Find that, and you will actually see the bridge just start rocking and rolling and literally tear itself apart. And there were actually a few motorists on the bridge who probably, I'm guessing, lost their lives because they couldn't get off, and went down into the deep, and sections of the bridge came tumbling down too. It was a study in engineering, and from then on design bridges taking into account what the prevailing winds are. The Verrazano Narrows Bridge, I think was the name of that one. Okay. That's all that's said about resonance, but that's what you're dealing with. So if any of you do get into MRI, then you're looking at the magnetic resonant imaging, and you're measuring change in magnetic field and how that reinforces. And you can see some really cool things with that. You'll think I'm a real basket case when it comes to health issues, but one time I had just one evening, I could feel my heartbeat and hear it beat. I mean, not just feel it like this. I could sense my heart beating. Right now, I know it's beating, but I could actually feel it beating. And I thought, what is going on here? And, after a while it passed, And about 13 years later, I had another one of those, and that time, and this panicky doctor that I had him for a doctor still, he had me get on the treadmill and he did the thing with that stress test, measuring my heart and stuff like this. And I was able to do everything he asked me. He said, oh, there. I see something right at the end. We need to do a angio. Say again? I think so. Is that where they insert the device up through you and? Yeah. Okay, he was going to do that. And my wife said, no way you're going to do that. That is very invasive, and it's happened twice in his life. I was in my probably 40s by then, 13 years apart. So then we got an appointment. That's the last time I used, shortly thereafter we changed insurance plans, so I changed to UAB's system. And but we knew a guy that goes to our church who was a cardiologist at UAB. Went to see him. He said, we'll do this. And this time I know it was what he called a nuclear test. And so he had me do the treadmill again, and they strange instructions. Let me know when you think you can only do a minute more. How will I know that? I'll know I can't do any more. How will I know I can only do a minute more? So I was going along, and finally the technician, called somebody and said, give them the shot. So they injected. They already had it all lined up. I did a minute more, and it was no problem. I didn't have any problem doing it. And so then then they had me lie on the table for some period of time. It seemed like a long time. It may have been 40 minutes, an hour, or something like that. And then they did the scan. Now, I don't remember which kind of scan it was. But then with the scan, and computer assisted. So I think would that be a CAT scan? Computer assisted tomography, is that what that's called? Whatever kind of scan it was, but they showed, here was your heart if we slice it this way, here's if we slice it this way, here's if we slice it this way, and this is what it's supposed to look like. Yours looks perfect in every way we slice it, you don't have any problems, much less invasive than, it was nothing. I mean, to me, just lying on the table waiting for them to do it. So, that was some type of scan. Well, it happened to be about 7 years later this time, I happened to be at the doctor's office when I had my book bag, and it was pretty heavy, and I was grading papers while I was waiting to see the doctor, and I had forgotten to bring something, and I got, mad at myself for forgetting that. As I was bending down, rifling through that, and it started again. Now, I don't know what made it happen, but it seemed like something to do with bending over like this, and maybe blood pressure went up a little or something. Started doing it again, so I went to see the doctor. my blood pressure, which usually is very low, all of a sudden the heartbeat was irregular, everything was wacko. I said, well, I'm just having one of these. I have them about every 7 to 13 years. This is my third time in my life I had it. And he wanted me to see his cardiologist, so I went back to see the cardiologist again. And this was the day, I don't know if y'all remember the day of the snowpocalypse. This was that day. They were, when it looked like I was going to be there long, I tried to call the college to tell them I wasn't going to be able to make my afternoon class because they were keeping me for this thing. I didn't know beans about what was going on outside. I couldn't get anybody at the college to answer a telephone. So what's going on? And someone said, well, they probably closed down. A lot of schools have closed. I said, why? It's snowing outside. Well, I heard it was supposed to be a light dusting. No, it's snowing big time. And sure enough, it was, they were getting ready to close the Kirkland Clinic. I was sitting around and, what are you doing here? We're getting ready to close. Well, they say come up here. Oh, okay. So they put me in, did all the thing. And when I finally got to see the doctor the next time after all the tests had come through, he said, oh, yeah, I've seen you before. It's nothing to worry about. So, but later that day, I walked because I couldn't drive all the way home. I had to walk up the last hill down home. Then my wife got stuck, so I had to turn around, walk back up the hill, and down, go pick her and another of her colleagues up, and drive back. That time we were 2 hills away. We walked all the way back to the house. And then the third colleague had spent an hour on the interstate and only gotten one exit, down the road, and had turned around and was going to spend the night in the office. She said, no, drive as close as you can. So I walked back and picked her up and came back. All after this, I had no problem. But I was so glad they had all these things to measure this. And some of them were sound, some of them were electrical impulses, some of them were nuclear responses. Okay. Blah, blah. Okay, let's go to simple harmonic motion. Now, this next slide has to do with it, but we're not there yet. Okay? Periodic motion occurs, and there's several other slides they could have shown, but they didn't. This is the last slide they're going to show. Periodic motion occurs when an object moves repeatedly over the same path in equal time intervals. Okay? Tons of things in physics, and you've experienced them too, go by simple harmonic motion. I mean, if you just think about it, light and dark, day, night, seasons, everything repeats itself in certain cycles. I mean, your heartbeat, that's one thing they were measuring. My heartbeat was not in a regular rhythm. By the way, what I had was not a heart fibrillation, but a heart flutter, which is different and I guess usually not very serious. Okay? But he said if it ever becomes serious, go immediately to the nearest fire station and have them put you on the EKG and send me the results right then while it's happening. Well, he got one pretty close to it himself, and it, knock on wood, I haven't had one for I don't know how many years now, so it's not anything I really worry about. But that's what simple harmonic motion is. It's the same repetition over and over. It's a lot like that what you have pushing the car off. Because another thing that's very similar to the resonance that we were talking about is when you're pushing someone on a swing, a kid on the swing. You don't want to push them when they're coming up to you. That's going to be hard on you and hard on them. Well, you wait until it gets at the peak of the thing, and right as it starts going down, then you give them a push, and they swing really high. And actually, you can go too high, so you sort of ease up on that because you're getting a resonance. But what you're doing, the swing it's just going back and forth as long as you don't push too hard at a very regular motion. Simple harmonic motion. Okay? Now, that's the type of motion in which the acceleration of an object is directly proportional to its displacement from the equilibrium position. Okay. Now notice there, acceleration and displacement. What's the thing we've left out in between those two? Remember we talked about displacement then we had something else, then we had acceleration. What's the missing piece? What does your speedometer measure? Velocity. Velocity, that's the missing piece. So what's happening then, when the displacement is, say, at its minimum, the acceleration is also at its minimum, but the velocity will be its maximum. And when the acceleration is at its maximum, or displacement at its maximum, the velocity will be at its minimum, usually 0, okay? So that's what's going on with this, and probably the best, or at least one good illustration of it, would be movement on a spring, okay? And that's the one they give in the text, okay? If you have a spring suspended from a beam up here somewhere, and you put a mass on it, it's going to stretch the spring to a certain amount. Whatever it settles out at, that's its equilibrium position, okay? If you stretch that spring and hold it, it's pulling back on you, okay, right? If you release that, then it goes up, goes through, past that equilibrium position, compresses, starts pushing down, and it just goes up and down and up and down and up and down. That's what a spring does. You could have started by compressing the spring, now it's pushing down on you. You release that, it goes past its equilibrium position, and goes up, down and up and down and up and down and up, okay? It does the same thing. That's simple harmonic motion. And if you think about it, wherever you stop that spring when you either stretched it or compressed it, your velocity is 0, right? But you have the maximum force, which would be the maximum acceleration, also the maximum displacement from the equilibrium position. So you see the displacement and the acceleration force are both at the maximum then, but your velocity is at 0, the minimum. But once you release it, then it starts, if it's up here compressing, the spring pushes down here stretch, it starts pulling up, but when it gets to equilibrium position, there's no more force on it. No more displacement from equilibrium. It's at equilibrium position. But that's where the speed's the greatest. Okay, so you see the displacement and the acceleration are in phase, and the velocity is exactly out of phase with it. That's what leads to simple harmonic motion. Okay. Now, displacement is how far it is from that equilibrium position. I'm reading or defining these highlighted bold words to you. Displacement of an object in simple harmonic motion is the distance from its equilibrium or rest position. That's its displacement. When it happens to be passing through that, it's 0. There it might be positive, here it's negative, or vice versa, however you set up your scale. The amplitude of the vibration is the maximum stretch or maximum compression, whichever, okay? That's the amplitude of the vibration. The period is the time it takes from one position all the way through the cycle back to the same position again, okay? That would be the, now it's not just position, okay? Let's say the equilibrium position. If that's where you're going to measure from, it's going to compress, come back. It's at equilibrium, but it's going in the opposite direction. So you have to wait till it gets down here, and when it's going back up, that's one period. It has to be not just the same position, but going in the same direction, at the same speed and everything, okay? So that would be your period. That's a time, just like we had for the other ways earlier. Time, the period is a time. The frequency, just like before, how it's frequently related to period, exactly the reciprocal. 1 over period is frequency, 1 over the frequency is period. It's the number of complete vibrations per unit time. So whereas period is the time for it to make one complete cycle, frequency is the cycles it takes per second, the number of cycles it does per time period, okay? Cycles per second. Now, this picture then shows a Ferris wheel. These are the sun's rays on the Ferris wheel. This is rather a strange way, but I guess it's showing it well. Simple harmonic motion of the shadow of a person. Okay, now I see what it's talking about. I thought, what does the sun rays have to do with it? Shown on the line PQ. Okay? If this is the person on the Ferris wheel, the sun shining down on him, and you can tell by looking at the shadow of that person where he is. Okay? Right then, his shadow is going to be right here. There's the shadow, somewhere between P and Q. Okay, Ferris wheel, let's say, is turning that way. So a little bit later, he's going to be up here at B. His shadow would be down here. And at C, it would be over here, as far out, close to P as you could get. And at D, you can hardly see him, he's right there. And E, back over here, pretty close to where he was A, not quite, but close. So his shadow is doing this. Started here, goes through the equilibrium position over here, comes back here, and it's just doing this back and forth and back and forth. Shadow is. Okay? That's simple harmonic motion, just like the spring. If you had a horizontal spring on a frictionless surface, it would just do this. Okay. Have you ever in your car had your shock absorbers go out? Probably not, huh? The shock, probably not, okay. The shock absorbers are what keeps your car from doing this, okay? When you run over a bump, you've seen some old cars that they go over a bump and then they do this for a while. That's simple harmonic motion. The shock absorbers dampen that and stop it. They stop it after, yes, okay. Maybe some of you have had shock absorbers go out on you. But that would be, without the shock absorbers, you have simple harmonic motion. The shock absorbers attenuate that. Okay. All right. Let's see if they show this next one. No, they don't. I already saw that. Another example of this is a pendulum. Okay? And a pendulum also exhibits simple harmonic motion. What a pendulum is some fixed point up here, and this can either be a string or a rod, and you have a thing here, and it goes back and forth and back and forth. Simple harmonic motion. Have you ever seen a grandfather clock? Yeah, that's a pendulum at the bottom. It just swings back and forth. Some music teachers use those things to keep you on time, you know. Those are things like pendulum. Okay? And they go on by simple harmonic motion. Here is a formula that relates to that. Now, if you remember from before, capital T was period. It's not just time, it's the time period of your simple harmonic motion. Is 2 pi times the square root of L over G. L being the length of that pendulum, and G being, of course, the acceleration due to gravity. Okay? G is 9.80 meters per second squared if you're in the SI units, 32 points, whatever it is in the other one. T is the period, usually in seconds. L is the length of the pendulum. It could either be meters or feet. And G is the acceleration due to gravity, 9.80 meters per second squared, or 32.2 feet per second squared. Most books I use just use 32. This one uses 32.2. So there's another sample of periodic motion. Okay? And they don't even give you a problem with that. Well, they do give you an example. Funny, I was just giving the illustration of swing set, pushing a kid on a swing. They say here, try this activity, swing set physics. Swing is often serves as a good pendulum. Using a stopwatch, measure the period of the swing as it moves forward, backward, and back, forward and back. Vary the amplitude of the swing, the mass of the person sitting on it, and the length of the swing's change. Which variable alters the period? The length of the thing, right here. The acceleration due to gravity is constant. The only thing that varies the period, Not how heavy the person is on the swing, nothing else, only the length of the pendulum. So here's example 1 in this section, and this relates to that. Find the length in centimeters of a pendulum with a period of 1.50 seconds. So this is what we're looking for. Okay. And what we have, this is 1.50 seconds. Okay. That's the period. Now they say in centimeters. So since we're in centimeters, we're going to use the, maybe not exactly SI, but the metric type measure. But since they're asking for centimeters, we can't use G in meters per second squared. We need it in centimeters per second squared. How many, let's do our conversion here. 9.80 meters per second squared. We're going to need to multiply that by something to give us some number in centimeters per second squared, because we need to have centimeters, not meters. So what unit are we going between? And to, from and to. Second squared, same on both sides, so it's not that. You're going from meters to centimeters. So here's our conversion factor. The first blank is for numbers. Don't worry about that. To always put the units in their place first. What unit is going to go where? Between meters and centimeters. Centimeters on top. I'll buy that. And meters on the bottom. Now match the numbers with the units. How many centimeters in a meter? How many meters in a centimeter? 100 centimeters makes 1 meter. So now we multiply numerators, divide by denominators. By the way, your meters cancel out, and you get 980 centimeters per second squared. Yeah, that sort of makes sense. So let's do our thing here. 2 pi. By the way, that's an angle. It has no units. It's radians. The square root of L, that's what we're looking for, over 980 centimeters per second squared. Okay. Now, I'm solving it the plug and chug method. You could have done the chug and plug. I don't care. But what we've got to do, what I would suggest doing is first dividing both sides by 2 pi. Let's get that out of the way. 2 pi. Okay? That'll wipe it out here. Then square both sides. So 1.50 seconds divided by 2 pi. Okay? You're going to square that whole number. Okay? And that will give you L over 980 centimeters per second squared. Right? Okay. Now, that's going to be some pretty small number, because pi is 3.14 approximately, and twice that is 6.28 approximately, and that's going to be divided into 1.25, which is 1.50, which is going to be a pretty small number. You square that, it gets even smaller, but then that number you're going to multiply by 980. Okay, so 980, and that's meters per second squared, multiplied by 1.50 over 2 pi squared, and that will have units of second squared. This second squared cancels out the per second squared. Sure enough, that's going to give you a unit of meters. Oh, I'm sorry, that's centimeters, not meters. Centimeters. Okay, that will give you how many centimeters long the thing will be. So, if you do that, 980 times 1.5 squared divided by 4, I can already square it too, divide that by pi squared. Pi squared is something fairly close to 10, but not exact. But anyway, just do the division and see what unit you get, what number you get. Anything? So 980 times 1.5 squared divided by 4, and then divide that by pi squared. What you get? Anyone got it yet? .5 squared is going to be something pretty close to, it's going to be 2.25 times 980. That's going to be something less than 220 divided by 4, which is going to be less than whatever. 55.85. Okay, they round it to 55.9 centimeters. Now that's got pretty long. That's a little over half a meter long. So that's a little bit longer than this, because this is about half a yard. Okay, it's called a cubit. That's how they measured Noah's Ark, was in cubits. Okay, half a yard approximately, and this is more than 6/10 that. So it's a pretty reasonable pendulum length. Now notice I went on and changed it to centimeters per second squared. In the book, they kept the meters per second squared, and they got 0.559 meters, and then converted that to centimeters by doing the same conversion we did. They just wrote it for you. And that finishes 16.6. And there's a problem set there. Have 14 problems. You can do any of the odds that you wish. There's a glossary here, pretty healthy glossary. It takes all of one page and a couple, 3 words on the next page. It has 5 formulas that you will use frequently. Some review questions, which are probably good. They're multiple choice, it looks like. The first 7 are multiple choice, and the next ones are just short answer, probably. And then review problems, and I'm guessing the odds are in the back on those. And then there's an applied concept, and look at that. I didn't realize it was in here. This, oh, I said it wrong. It's not Verrazano Narrows, it's Tacoma Narrows Bridge across Puget Sound in Washington, not Oregon. Sorry, had it wrong. Tacoma Narrows Bridge. They called it Galloping Gertie, okay? And I think you can probably see some old movie footage of that. But look at that moving. And shortly after that picture was taken, I think it pulled itself apart. I would not have wanted to be driving on that. Probably at any time. So there's several applied concepts there. You can look at those. Any questions? Chapter 16. Now, I didn't have your test ready today. My office hours disappeared on me today. Got an email from the Vice President's office that we had a person from the National Science Foundation on campus, here on this campus, of course, and they wanted several of us to be there to meet with them for lunch, to meet them and get a discussion going and that kind of stuff. So as soon as my first class was over with, I had to leave campus, Bessemer, to come over here. They were late getting to the lunch time, so therefore they were late when the lunch was over, and then I had to rush back to the Bessemer campus to do my second class, and then did the second class, and then rushed over here for the third class. So my office hours a day were either in a meeting or driving back and forth between campuses. So, sorry I didn't get to make out the test. I will try to do that. Tomorrow I've got office hours between 10:45 and 1:15. So hopefully I can get your Chapter 16 test made up in that time. I'll try to bring that with me on Wednesday evening. Okay. So let's move on to any questions on chapter 16? Sound. Waves and sound. What was the title of it? Wave motion and sound, yeah. Okay. Which I think will be a pretty important chapter for you when you start doing your sonography. Okay. Not that they'll go into as much detail as we did, but to know the background information, I think, is usually helps you understand what's going on. We're moving now to basic electricity, chapter 17. And I don't know if you noticed that, but what we've got left to do is 17, 18, 19, and that's it. Now, we don't have that much time. These are huge chapters, okay? 17 has 13 sections in it, 18 has 7, and 19 has 10. Don't believe we're going to get all those done. So we're going to hit the ones that are most appropriate for what I saw in the course description for this course. So we're going to start in 17.4. Anything we need from the first sections, we will come back and pick up, okay? So what I'm going to do is, and this is such lousy PowerPoint, I'm going to see if I can find where 17.4 begins. And I'm doing this let me find something in 17.4. Whoops, I went right past it. These are fairly short sections, though. Okay, we passed that. I think past that. I think we're beyond it. Okay, let's look at this and see what that is. See if we can find that. Yeah. Okay. All right. Looking at this, it looks like there are 0 slides from 17.4. Yep. Believe I'm right on that. Okay. So we'll start there. There's 1726, and that's 1719. Oh, wait. Maybe I'm wrong. That's 17.8. I know that's in the previous section. 17.3. Yeah. Okay. This is really great PowerPoint, isn't it? Okay. So we'll start on this one. Okay. Slideshow from current slide. Okay. We're not ready for this yet. We'll get there in a few minutes. Let's first talk about electric fields. That was one of the things that was mentioned in the course description. First sentence is not very accurate. So far we have discussed electrification due to brushing electrons from a surface. Okay? The concept of electric field is an important part of the study of static electricity. Okay. Let's back off and sort of catch up where we are now, where we are in the text. There's 2 types of electricity. The first, and for centuries, the only one anyone really knew anything about, and they didn't even have the title for it, was what we call static electricity. And that's what they were talking about. That is the rubbing off of charge from one object to another object and setting up potential to shock you, okay? And the earliest uses for electricity was in parlor games, when a group of people would be around and someone would have a piece of amber. I don't know if you know what amber is. It's fossilized rosin from tree sap, that changed into a sort of a clearish amber color that sometimes we have bugs suspended in it. I don't know if you've ever seen that, but that's what amber is. If you take amber, quite often it'll be in sort of a rod-type shape, and rub it with some type of fur, any kind of fur. It basically is knocking, and they didn't know this at the time, knocking electrons off the fur onto the amber. Okay? So you've got a buildup of electrons there. And then someone sitting, talking, or playing cards or something, you take and touch the amber to them, and they get shocked. And sometimes you can actually see a little spark go across. And it's nothing serious. And it just shocks me. Ha ha ha! Okay, well, that's funny. Okay, and that was about all people understood of electricity for centuries, is that you could do things like this. At some later point, they realized if you took glass, a glass rod, and rub it with silk, you get the same thing. But then I think the silk gets the electrons off the glass, and the glass is left with a deficit of electrons. Okay? And then if you had a piece of charged amber and charged glass, and suspended them, on something they were hanging there, brought them close, they would attract each other. Obviously, they're opposite charges, okay? But if you had two pieces of amber and you brought them close to each other, they're going to try to get as far away from each other as they could, okay? So that was the whole principle of static electricity. Now, you know about static electricity, I bet. Ever pull things out of the dryer and can hardly pull them apart. And when you pull them apart, you hear, and if you did it in a dark room, you actually see little sparks. You've seen that? That's static electricity. The whole act of the drying and stuff, some materials have rubbed into others, dissimilar materials. Some of them have attracted electrons off the others, or, lost electrons to them, whichever. And they set up opposite charges and they stick to each other like crazy. Okay? Now, some aggravating instances of this. Have you ever opened a cellophane wrapper of something, pulled it open, and got out your crackers or whatever, and then went to throw away the cellophane? And it won't. It climbs all over your hands. It feels icky. You cannot shake that thing off, okay? And you pull it with this one, now it's stuck to this one. It's one of the most aggravating things. It doesn't hurt at all, but that's an example of static electricity, okay? When that act of ripping it, you separated electrons from one piece of another. Now it gets charged one way, you're charged another. And I was doing radon research at Southern Research Institute in downtown Birmingham, or Southside Birmingham. We used to stay at pretty cheap hotels when we were down in Florida or other places, because we were trying to use our research dollars as best we could. And we were all guys, we didn't care. And they were okay hotels, but they always had this cheap polyester carpet, and you do along, say, with rubber-soled shoes or whatever, and then reach for the doorknob and get shocked like crazy. Okay? That's static electricity. Your feet on the polyester carpet, rubbing electrons off one on the other, probably off the carpet onto your shoes. You build up an excess, you reach for the doorknob, and that discharges. Static electricity. Okay? Now, what causes that, and all kinds of movement of charges, though static is not moving until it goes to discharge, is anytime there is excess charge of one type or another, whenever there's a charge, there's a field around that charge. The field is not something you see. It's almost like it's an imagined thing, but it's always there. Okay, so it's not really imagined. They really are there. And that's what this section is talking about, the electric field. In terms of static electricity, like we talked about, an electric field exists where an electric force, okay, now you remember forces from before? a push or a pull, okay? An electric force, and this could be of attraction if they're opposite charges, or repulsion if it's the same charges. The force acts on a charge brought into an area, okay? Now, they give the example in the book, and this was the figure I was looking for, but they don't show it in the slide set. I don't know if you've seen this happen before. Someone blow up a balloon, and take the balloon, and if you got some hair, okay. It's not that funny. Okay.
It was, because it said, okay.
And rub the balloon on your hair. Now, you need fairly clean hair. If you haven't washed it in a few days, it might not work as well, because oily hair doesn't do as well with this. And you also need it to be very dry hair, okay? A lot of humid air, it's not going to work well. But if it's nice, dry, and you rub it, and then you can stick the balloon to the wall. And that's what the figure at the bottom of page 457 is showing. That balloon's just stuck to the wall there. Why? Because when you rubbed it against your hair, you probably got electrons off your hair. If it wasn't oily or damp, or the air wasn't too damp, and got excess electrons on the balloon, the wall was neutral charge, and then it stuck because they were unlike charges. Okay? So what they're saying here, the force that's holding that on the wall is related to the field. The charged balloon put on the wall illustrates this principle. Notice the balloon attracts the wall even without physical contact. Actually, the wall attracts the balloon. I mean, the wall doesn't come toward the balloon. You hold the balloon and get close to the wall, you'll see the balloon moving toward the wall. And then ultimately it'll stick when you let it get there. Okay? Hopefully it's not going to pull the wall. No, okay. The balloon attracts the wall without physical contact. The balloon has acquired a negative charge through friction, but the wall surface acquires a positive charge produced by the electric field of the balloon. Now, what they mean by that, the wall doesn't suddenly become positive, but when you bring a negative balloon near it, the positive charges that are in the paint or whatever tend to come toward the negative charges, and the negative charges try to go as far away. So that's what makes the wall polarized, a change of the distribution of charge on the wall. Okay? And that's what sticks it to the wall. Okay? Static electricity can be a real hazard in industry as well as a curiosity or sometimes a nuisance in daily life. Electric spark from static electricity, particularly from synthetic fibers at a textile mill, is extremely dangerous. I mean, these sparks can be fairly good. Actually, when we were at the cheap hotels and you went up and you had been shocked enough times you finally remembered, what you do is get your key in your hand and go up and let the key get close to the doorknob. And you can sometimes, especially if it's dark outside, see the spark and sometimes hear the spark jump from the key to the door or vice versa, whichever it is, usually from, I think, from the key to the door. Why does that happen? Because you don't feel the shock now. The shock is coming between this. There's the potential difference. The electrons, excess electrons are moved on to the key, no longer on you, so therefore that discharges, you don't feel a thing. Okay? Now, I don't know if any of you, in the old days, some of the old car seats, what did they call that, Naugahyde or something like that? It was a plastic, synthetic plastic, sort of made to look like leather, but it really wasn't leather anywhere close to it. But sometimes with polyester pants or something, you slide it all across that and reach for the doorknob and get a shock that way. Okay, that occasionally happened. And sometimes when you were charged like that, especially if you had on rubber-soled shoes that were pretty good insulators, and you went to fill up with gas, and you happened to discharge right as the gas fumes were there were not very frequently, there were reports of sometimes discharges like that actually created explosions. I never heard of very many, but I heard there were actually places at some service stations where they wanted you to touch this before you reach for the gas. In other words, discharge before you started messing with the gas. Now, this is a totally different story. It's not static electricity, but just to talk about, that synthetic fiber textile mills. I don't know if you've ever been in a mill, but there's usually dust all over in the air. If you got spinning fabrics, cloths and threads and things like this, usually there's dust in the air. Okay? And quite often that dust is flammable. Now, I had an uncle, I never knew him, that I know. It wasn't blood kin. He married to my father's sister, the same one that had what they thought was a aneurysm. But his youngest child was my age, and he had died shortly after Robert was born. So if I ever saw him, I was so young I don't remember him at all. But he had worked at a furniture, and this is Thomasville, North Carolina, where furniture. So they were always sanding and shaping and doing all sorts of things to wood products. So there was just fine sawdust in the air all the time. And they didn't know exactly what happened. They think someone hit a light bulb with a piece of wood by mistake. They were doing something, and when it blew, it arced, and the entire shop just blew up because all that fine sawdust in the air was extraordinarily explosive, and he died in that accident. But so when they say a textile mill, I can imagine almost that level of dust around. You don't want static electricity building up. And with things spinning and turning, rubbing and stuff, you don't want sparks in that kind of an environment. Okay? So, anyway, enough sad stories for today. Okay? But the electric field exists where an electric force of attraction or repulsion acts on a charge brought into the area. So this is actually how they define an electric field. Let's say we had some charge up here. You want it to be positive or negative? Positive. Some positive charge up here. Okay? Just hanging around out there. Now, you have a little test charge. Your test charges are always positive. Always. The test charge is always a small positive charge. If you're trying to bring that charge into the presence of that positive charge, what are you going to feel? What about like charges? They repel each other. So therefore, the force is going to be in that direction, pushing against you. The direction that force is, that's the direction of the field. And wherever you're bringing that in, it was going to be pushing against. Now, if that was a small negative charge up here, or some sort of negative charge, your test charge is always positive, right? Bring that in, what's happening? Is wanting to go this way, so you're having to pull back. So the force is in that direction. So your field lines are always in the direction that the force would be on a small positive charge. If you've got a charge somewhere, if it's positive, it always has field lines pointing away from it. If it's a negative charge, it always has field lines pointing toward it. That's how we picture the field lines. We picture them as the lines of those forces, either toward or away from the charge. So that's how we define the field. Okay. Electric fields can be measured by using test charges, and I wish they had some of these illustrations there. If you have small positive charges, say in a spherical shape, the field lines are always pointing away from those. Small negative charges in a spherical shape, the field lines are always pointing toward those. Okay? What's that? On page 458, top of the page. Okay? And here is your first formula here. They don't actually say it is one, but it is. Here's how we define the strength of the field, electric field. All right. The electric field is defined to be the force per unit charge. Okay? And they actually call this Q prime, which is that. So E is the electric field. F is the electric force. And Q prime is the test charge measured in coulombs. Capital C for coulombs. Why? Named after a person, Charles Coulomb. Happened to be Charles Coulomb, French physicist who did a lot of the early studies of charge. Now, the funny thing is they didn't give you the other units. Force, of course, is measured. Anyone remember what force is measured in? Second? Newtons, exactly. And the field lines would then be in newtons per coulomb. Okay? It doesn't have a special unit for it, just newtons per coulomb. Now, later we'll see another definition of that with different units, but they work out to be the same. Okay? Now, remember earlier I told you the difference between vectors and scalars? Not that this book is going to make a big deal about it, but fields are always scalar because they're always directional. Forces are vectors because it's directional. Forces are always vectors. They're directional. Okay? Charge is not. Charge is just a scalar quantity. Coulombs. Okay. The result is a vector quantity. They do mention that. That is the magnitude of the electric field. So let's do example 1 then. A positive test charge of 30.0 microcoulombs. So this is your Q prime. The test charge is 30.0 microcoulombs. Boy, does anyone remember what the prefix micro stands for? 10 to the minus 6. That's a millionth of a coulomb. It's a pretty small test charge. Okay, 10 to the 30 microcoulombs. It's placed in an electric field. The force on it is 60 newtons. So the force, F, is 0.0600 newtons. 0.600 newtons. Now, that first zero in front of the decimal point is never significant. Unless there's a 1 or 17 or something in front of it, then it would be. But that just lets you know that period there is a decimal. It's not this period at the end of the previous sentence. That's that. The 2 zeros after the 6, they are significant. You wouldn't write them down unless they were. So this is good to 3 decimal places, as is your 30.0 coulombs, the charge. Why is that? Because 3 is obviously significant, and the one after the decimal is significant, so therefore the one in between has to be significant too. Okay. So what's your electric field at that location of the test charge? Pretty straightforward. E is equal to F over Q, Q prime. Okay? And your force is 0.600 newtons divided by, I'll write it out in scientific notation, 30.0 microcoulombs. That's times 10 to the minus 6 coulombs. That's what micro means, 10 to the minus 6. Okay, now if you got a calculator, you know how to do scientific notation, right?
I have a question.
What's that?
In the book it says 10 to the minus 5.
Oh, I can't read, can I?
No, I didn't
You're
know
right.
if it was wrong.
No. Okay. Notice what I said. I said 30 because this is 30 microcoulombs.
Okay.
I said 30.0 times 10 to the minus 6. 10 to the minus 6 means micro.
Right.
Now, they wrote it by moving the decimal one place this way, making a smaller number here, so you have to make this a bigger number. It was -6, make it -5.
Okay.
So yeah, it's the same. That's
Okay.
the same. I just wrote it there because that's what micro means, is 10 to the -6.
Okay.
They wrote it in true scientific notation. This is not scientific notation.
Okay.
3.00 is scientific, but 10 to the -5. You're right. It's going to give you the same answer. So with your calculator, whichever one you want to write, one in the book or this one, 0.600 divided by, and if you use the 30, it's 30. You don't need to put the 0.0 in your calculator. EE or EXP minus in parentheses, not the subtraction key, but that minus key, 6, and that follows that. Or if you use the other one, it would be 3 EE or EXP minus 5. You're going to get the same thing. Divided by that, and what do you get? Another day older and deeper in debt. No. This will be, I'm going to do some strange things here. I'm going to write this as 0.600 newtons divided by 0.1234300 coulombs. That's 3 times 10 to the -1, 2, 3, 4. Oops, I need one more. No, that was right. 5, 6. Okay, yeah. That's a blob in there. It's not a... I had it right to begin with, and now too much erased. Okay. All right. Now, I'm going to move this decimal 5 places over, and that moves this decimal. I have to put some extra zeros there that are not significant 5 places over. Okay. And then 3 will go into 60,000, 20,000 times. So what's our electric field there? 20,000 newtons per coulomb. Whoa! Okay. And they say 2.00 times 10 to the 4th newtons per coulomb. That's the same thing. And actually only to that 0 is significant. Same answer, 2.00 times 10 to the 4th newtons per coulomb. That to me sounds like a pretty strong electric field, okay? Because when you saw that much force, so it didn't seem like a lot, 0.6 of a newton, but acting on that small of a charge, that had to have a pretty strong field. Okay, do you see how that works? All right. Now, I wish this next figure were here, but it's not. This is figure 17.12. This is some pretty old technology here, if you're looking in your book. These are the old electron picture tubes. Now everything's plasma, flat screen. Nobody sees these anymore. But notice I actually had an old computer monitor that sat that deep in the desk because it had that. Now I have a flat screen, almost as flat as my laptop is. Okay, almost that flat. Okay, but this is exactly the type of thing. The field is being bent by, and this is how they do. And actually, what you don't realize is when you're seeing those pictures on the screen, what's going on behind the screen is just a series of very fast images going left to right, right to left, something like that, up and down and stuff like this. And you're seeing these things change almost instantly, but it's not. It's finite, but your eyes don't catch that, and you're seeing the picture move and stuff like that. There's a physics connection here on lightning safety. The Earth experiences about 25 lightning ground strikes every second. That's the whole Earth. So probably right now that's out in the Atlantic Ocean somewhere. There was a bunch of them, that storm that just went past the other night. We were hearing a bunch of those, what was it, about 2 or 3 nights ago? I mean, it seemed like getting most of those 25 lightning ground strikes every second. We were getting a good number. Each year in the United States, approximately 400 people are struck by lightning, which results in about 100 deaths. And the reason for that, you know the reason that people get killed by lightning? We are electrical machines, right? Everything about us is controlled by electricity. Every neuron in your body has a small positive, actually two small positive charges, one sodium and one potassium. There's ever so slight difference between them, and signals are sent by that potential difference all over. So what you're hearing me say that's coming into your eardrums, being translated by your brain, it's all being done electrically. My speaking to you is done electrically. My heart pumping the blood, the messages are sent electrically. That's why the punishments for capital crimes at one time was the electric chair. Okay? What they did, they sent large currents through you, and that disrupted the electrical operation of your system, and you died. And electric ground to lightning, cloud to ground, or ground to cloud strikes. Anytime it hits the ground, if you're in that path, that's a lot of voltage, which creates a fair amount of current in you because you got a lot of charge in you, and that just overloads your circuit, and it gets you. We've had cattle in the field who have been struck by lightning, and the vet said if you did an autopsy, you'd see their heart was like 2 or 3 times the size normal, because that lightning just blew things up, and so yeah, it's very strong electric fields. They show this guy on the golf course covering his ears, and actually I guess this is what you're supposed to do. If you see or hear lightning, he's heard thunder. That means lightning is close enough for you to hear the thunder. Get as low as you can go. Should he run, get under the trees? No! Okay. She should get down in something. He got down in the sand pit as low as he can get. Not a bad idea. And get to be as low a profile as possible. You don't want to give the lightning a good target to get to the ground easier. Because guess what? You're a really good conductor of electricity. You have, the blood is filled with salts, and salts in water make great conductors. Okay? And your blood is mostly water with salts. So you're a pretty good conductor. All right, that was section 7.4, which was electric fields. There are 8 questions. I know the odds, I think, have the answers in the back. So work on those. All right, let's at least get started on simple circuits. And this was another thing that was mentioned in your course description. So I have a feeling this is going to be fairly important to you. Okay, there's 2 types. Okay. One thing we talked about was static electricity. You build up charge on one object, not on another. The balloon on the wall, the different pieces of fabric out of your clothes dryer, all that can be static electricity. Well, what if you have moving charges? And this is when finally we found out, hey, we can use this stuff that used to be a parlor game, we can use it to our advantage. Okay? Now, actually, I'll give a little bit of background here. We don't have time to do too much of this. If you're medically related, you may be pleased to hear that the first hint at some useful purpose here came not from a physicist, but from an anatomist. Someone studying the anatomy of frog legs. Okay? Literally. Okay? This guy's name was Luigi Galvani. Good Italian name, right? And he was an anatomist and trying to understand, and he had this dead frog that had been stored in formaldehyde to keep him from rotting. though a rotten frog would smell much worse than formaldehyde, but nevertheless, But anyway, it kept him preserved. And he had cut the leg off of the dead frog. The frog had been dead for a long time, cut the leg off, and he was studying the structure of the muscle of the frog leg that had been severed from the body of the frog. And he had some little tweezers he was holding. I'm just going to guess that they were probably copper, okay? But he had a little probe that he was trying to separate the muscle tissue from the blood vessels, and if he could see the little nerve tissue, he was trying to separate those. So he had a little probe, sharp little pointed thing, and I think it was probably happened to be an iron. Huh? It could be zinc. Oh, was it zinc? Well, he's looking at this, okay? It could be copper and zinc. Or it was just two dissimilar metals. So he was holding with the tweezers with one metal and probing with this, and suddenly the frog leg twitched as he was doing. Yes, that's exactly what he thought. After he emptied his after he thought about this, he said, "I've just discovered life. I've created life. This was a dead frog; had been dead a long time, and suddenly I've just made it come to life again. I'm going to be famous." So he started trying to experiment like a good scientist would do, and he found out when he had wood tweezers and whatever kind of probe that he could get a good effect. And when he had iron tweezers and iron probe, he couldn't get a thing. It's only when he had dissimilar metals, so now he hadn't discovered the origin of life, he had discovered something else. Well, this fellow countryman of his named Alessandro Volta, okay? Volta. Ring a bell? He read about what, and of course the anatomist, once he discovered it was a new life form or something, he went back to studying muscle tissues and blood tissues. But Volta said, "Hey, this is promising." So he started experimenting with, and he put together formaldehyde being a conducting fluid. Maybe that's required too. So he started using dissimilar metal types, plates of dissimilar metals like copper and zinc, with a material in between soaked in some electrolyte, like salt water or formaldehyde or something, and he could build up potential differences. This created the first batteries. And actually what Galvani had discovered was a battery. Two different metals with a conducting fluid in between, and that created a current that made the frog leg twitch. Okay? Scared him out of his pants. Okay? But it happened. But then Volta started studying this in general, studying different metals he could use. Some didn't make much charge, some had great potential differences. So he really did a good study of that. Now, he was from the northern part of Italy, Lake Como. Okay? It's a three-finger lake, and the other two lakes have names too. Como is one, very pretty around there, very close to the Swiss border, so it's very northern Italy, up into sort of the mountainous areas, not really the Alps yet, but almost into them. And fortunately, my wife had professional meetings at Lake Como one summer that was right in between the terms, either right between spring and summer or summer and fall. It was that week, and I was off, so I got to go, and she took a niece with her, and niece and I got to travel around and look around, be tourists, while she was busy at her meeting. Oh, shucks, you had to put up with it. But we went by this one place. It's a beautiful little, almost like a monument of some nature. And we went by there, and sure enough, it was a monument to Alessandro Volta. and we went to tour around inside, and we saw some of, they called them the pals then, and the ones he studied and put together and read a lot of, he did a lot of other stuff too, but he was one of the first early researchers in electricity. And guess what unit they named after him? The volt, yes. And Alessandro Volta, they named the volt after him. And I guess that story used the rest of the time we had. So we'll start next time on in section 17.5. I guess I should make a mark there too, so I'll know where we are. And we'll talk about the two different kinds of currents that you can form. Okay. So, any questions? And we'll do 17.5, and that's a fairly short section, 17.6.
So are you bringing in the 16 test on Wednesday?
I'll bring in the 16 test on Wednesday. And we'll talk about 17.7 series circuits, 17.8 parallel circuits, and 17.9 maybe compound circuit. I don't know how much circuitry you need. Let me see what I wrote down. Yeah. Actually, it says here we'll skip Ohm's law. We'll do 7.4, 7.5, and then we'll do 7.7, 8, and 9. 17, 7, 8, and 9. All right, good deal. Any last questions? Parting shots?